friends? Well, we have completely understood if we have a non-homogeneous system of n linear equations and n unknowns, what are the all possible conclusions which we can derive about the nature of the solution of such system. How? If I just consider a non-homogeneous system of n linear equations in n unknowns as Ax equals b. You all know that any system of linear equations can be expressed in the form of matrix equation. So right now we all have considered a non-homogeneous system of n linear equations in n unknowns expressed as Ax equals b, where A is the coefficient matrix of this system. Now you know that whenever you have such a system, there are two things which you can say about the determinant of the coefficient matrix A, because in such a case, coefficient matrix A is a square matrix of order n. So, either the determinant of A can be non-zero, or you can say that the determinant of A is 0. Now, let us discuss about each of the cases, because we have already understood the conclusions which we can derive when such cases arise. So, if you have determinant of the coefficient matrix of this non-homogeneous system of n equations in n unknowns to be not equal to 0, that means when the coefficient matrix is a non-singular matrix, whenever the coefficient matrix is invertible square matrix, what can you say in this case? If such is the case with the coefficient matrix of the system is definitely consistent. Plus, consistent just means that it has at least one solution, but this system then becomes consistent with a unique solution. And what is that unique solution? This. The solution capital X, which basically on getting plugged in over here satisfies this matrix equation, is given by A inverse B. Now over here, if I tell you A inverse is nothing but 1 upon determinant of A times adjoint of the matrix A. So into B turns out to make this expression like this. So X is equal to 1 upon determinant of A times adjoint of A into B. Now here we observed two different types of cases arose. What were those two cases? The numerator you can see of this is adjoint of A into B, right? Determinant of A is given to you to be non-zero if the numerator matrix, right, or I should say this is nothing but 1 upon determinant of A times the matrix adjoint of A into B. So if this matrix turns out to be a null matrix of order n cross 1, in that case, if you divide each and every element of this null matrix by determinant of A, again it is going to give you 0. So if you have adjoint of A into B to be equal to null matrix of order n cross 1. So let me express this as one of the possibilities which can arise. So if you have understood that such will be the very structure of my solution X, I can have two possibilities, that adjoint of A into B is a null matrix of order n cross 1, or I can have adjoint of A into B to be not equal to null matrix of order n cross 1. If it is equal to null matrix of order n cross 1, divide each and every element of this null matrix of order n cross 1 by determinant of A, which is a non-zero quantity, you again get a null matrix of order n cross 1. So this is going to imply that system is consistent with trivial solution as the unique solution. I know there will be unique solution in this case, but in this particular case, Subcase, basically I should say, there will be the trivial solution which will be that unique solution. x1 equals x2 equals x3 and so on up till xn equals to 0. That is what is my trivial solution. So this is the conclusion which we can derive if adjoint of A into B is a null matrix of order n cross 1. If adjoint of A into B is not equal to null matrix of order n cross 1, then if you divide each and every element by determinant of A, again it will not be a null matrix of order n cross 1. This means not all entries of X will be 0. That means here also the system will be consistent with a unique solution, but this time that unique solution will be a non-trivial solution. By which I mean that not all the values of the unknown variables will be 0. There will be at least one value of at least one unknown variable which will be non-zero. Once entirely the conclusion about this particular case has been discussed, let's move on to the discussion of this particular case. Now, if you have determinant of A to be equal to 0, there are again two cases which can arise. One case is that adjoint of A into B is not equal to null matrix of order n cross 1. If along with the determinant of A being equal to 0, adjoint of A into B is not equal to null matrix of order n cross 1, this implies system is inconsistent that means there is no solution. Correct? And if you have adjoint of A into B to be equal to null matrix of order n cross 1, that means if along with determinant of A being equal to 0, adjoint of A into B is also equal to null matrix of order n cross 1, this means system is consistent, this time consistent with infinitely many solutions. These are all the conclusions which can be derived about the solution of a non-homogeneous system of n linear equations and n unknowns expressed in the matrix form Ax equals B depending upon the determinant of the coefficient matrix A. The question is, for example, I am in such a case. For example, I am in this case wherein I know there are infinitely many solutions existing. The question comes out as to how to proceed to find those infinitely many solutions. And so, we are now going to discuss a perfect algorithm which is going to pave the path, as in which is the direction in which you have to move to solve a non-homogeneous system of n linear equations and n unknowns. And if you have derived the conclusions about the nature of the solutions of the system, how to actually find those solutions will also be clear by this algorithm. So let's begin the algorithm. What does the algorithm's first step say? So first of all, let us just generally write that let Ax equals B represent a non-homogeneous system of n equations in n unknowns. Now see, if I am first of all writing this only, that means I had a system of equations in elaborative form and I expressed it in the form of Ax equals B. We are always interested in expressing our system of equations in matrix equation form, because the moment things are expressed in matrix equation form, my coefficient matrix come into picture, and then I can talk about its determinant and use the theory of its determinant to obtain the nature of the solutions of this system. So because I am focusing on the theory of determinant of a square matrix, I want that square matrix to come into picture, and so I want that my system of equations should be expressed in the matrix form. That is why the first step, if I would not have written this general thing which I am assuming, the first step happens to be that obtain the system of simultaneous equations and express it in matrix form or matrix equation form. So if you have not done this, the first step says do this. You have a system of equations, express it in matrix equation form to obtain the equation like Ax equals B for some coefficient matrix A. What you do in step 2? Algorithm says that in step 2, what you do is, the moment you have expressed it in the matrix equation form, you know that you have your coefficient matrix in picture. So what you do in step 2 is find determinant of the coefficient matrix of the very system of equations which you are dealing with. Once you have found the determinant of A, once you have found that unique real number which is associated to the coefficient matrix A, which is the square matrix associated to the system, what you do in step 3 is analyze that determinant value. If that determinant value is 0, then what happens? How you have to proceed? If that determinant's value is non-zero, then what happens? How you have to proceed? So step 3 says that if determinant of A is not equal to 0, suppose you have got a non-zero value as the determinant of the coefficient matrix of the system. So if determinant of A is not equal to 0, then the system is consistent with unique solution. This is something which we already know. We just discussed it in this elaborative branch form of conclusion of solutions, that whenever determinant of A is non-zero, the system is consistent with unique solution. This is the conclusion which is drawn about the nature of the solution. I am not getting my exact solution, and so the next line would be specifying as to how you have to obtain that very unique solution. This algorithm basically tells you that okay, the system is consistent with unique solution, but also gives you steps to obtain that unique solution so that you can have that one solution with you when you know there is a unique solution. So this says further that to obtain the solution, compute A inverse. Now A is a square matrix of order n whose determinant is not equal to 0, that means A is non-singular, which means A inverse exists. Such matrices A inverse, such matrices inverse matrix, we know how to find. So compute A inverse by using 1 upon determinant of A times adjoint of A. That is what you have to do. The first thing that you have to do is compute A inverse by using this formula, and then use the formula x equals A inverse B. This is what is the job of an algorithm. If you have determinant of A not equal to 0, you are not just supposed to conclude that this system has a unique solution. In fact, you can move further and obtain that unique solution by first of all finding the inverse, by finding such a very matrix, which is 1 upon determinant of A times adjoint of A matrix. Once you have obtained that, multiply it by B. Post multiply it by B, what you obtain is an n cross 1 matrix, which is nothing but your X, right, which is going to satisfy the very matrix equation Ax equals B, and only this X will be satisfying Ax equals B, because in such a case there is a unique X which exists. If omega is a complex cube root of unity, then the value of this determinant is what? Now the moment I say omega is cube root of unity, the properties of that should pop up in your mind. It is 1 plus omega square is 0, and you can very easily see each row has 1 omega in omega square, right? So I am going to say, if I say that column 1 goes to column 1 plus column 2 plus column 3, I am going to get this determinant being equal to 1 plus omega square, which is 0, rest same. Then again omega plus omega square plus 1, which is 0, rest same. And omega square plus 1 plus omega, which is 0, rest same. The moment you have one complete column to be equal to 0, your answer is actually completely nothing but 0. The only thing of point over here was that 1 plus omega square happens to be 0 when omega is cube root of unity. Next question says that the number of values of k for which this system of equations has infinitely many solutions. Now, you are given two equations and it is said that this has infinitely many solutions. By Cramer's rule, if you recall that infinitely many solutions, if this system has, that means d equals 0, d1 equals 0, d2 equals 0. What do I mean by this? d is 0 and d1 is 0 and d2 is 0. What is d? The determinant of the coefficient matrix, which is k plus 1, k, 8 and k plus 3. This determinant is 0, and when you replace the first column by this particular, I can say column vector. What? First column you replace by 4k, 3k minus 1, and next keep the same 8k plus 3. This is 0, and when you replace the second column by 4k and 3k minus 1. This is your d2, and the first column remains the very same. You are replacing the second column, first remains the same, k plus 1 and k. This is 0. Very easily you can expand this. You are going to get k plus 1, k plus 3 minus 8k is 0, and 4k into k plus 3 minus 8 into 3k minus 1 is 0, and k plus 1 into 3k minus 1 minus 4k into k is 0. When you solve this, you get k equals 1 and 3. When you solve this, you get k equals 1 and 2. And when you solve this, you get k equals 1. So what is the value of k for which this is 0, this is 0 and this is 0? It is only one value, which is the number 1. For k equals 1, this is 0 and this is 0. That's the common solution to all these three equations, and therefore it is for k equals 1 that this particular system is going to have infinitely many solutions. So your answer is k equals 1. Moving on to the next, we have fx is given to us in the form of determinant f of 3x minus f of x is what then? Okay, so here if I talk about this particular determinant, you can again see I have x plus lambda xx, x plus lambda xx, again x plus lambda xx. So I am again going to go for the same operation. Column 1 goes to column 1 plus column 2 plus column 3. So my determinant is x plus lambda plus x, which is 3x plus lambda. And then you have x, x. Then again in the next row here you have 3x plus lambda, x plus lambda, x, And again you have 3x plus lambda, x and x plus lambda. 3x plus lambda can come out common. I am left with 1, 1, 1, x, x plus lambda, x, 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 x plus lambda. Rho 2 goes to rho 2 minus rho 1. Rho 3 goes to rho 3 minus rho 1. When you do this, that's obvious operation because I want a 0 over here. 1 minus 1 is 0, 1 minus 1 is 0. So that's what I am doing. 1x, x, then you have 1 minus 1, 0. X plus lambda minus x is lambda and x minus x is 0. So you have 0, lambda, 0. 1 minus 1 is 0. X plus lambda minus x is lambda and x minus x is 0. Then 1 minus 1 is 0. X minus x is 0. And x plus lambda minus x is lambda. What is this determinant? This is nothing but lambda square minus 0, which is lambda square. And outside you already have 3x plus lambda. Right? So you have lambda squared into 3x plus lambda as your f of x. So what will be f of 3x? In place of x put 3x, you get 9x plus lambda into lambda square. Therefore, f of 3x minus f of x. That's what we need to find. F of 3x minus f of x is what? F of 3x lambda square 9x plus lambda minus f of x, which is lambda squared 3x plus lambda. So lambda square common plus, or this is minus 3x minus lambda because we want to subtract it, right? Plus lambda minus lambda cancels. You have 9x minus 3x, which is 6x into lambda squared, and therefore this quantity is coming out to be equal to 6x into lambda square. Nothing great, I just used the very operations to evaluate determinant and I got my answer. Next you have question number 4. The value of this particular determinant where A, B, C are actually the pth, qth and rth terms of a harmonic progression. Okay. If A, B, C are p, q and rth terms of an HP, then they are actually p, q and rth terms, or I should say their reciprocals are the p, q and rth terms of the corresponding AP. So let A be the first term and D be the common difference of the corresponding arithmetic progression of this HP. Then if small a is the pth term of this HP, then 1 upon a is actually pth term of this AP, which is a plus p minus 1d. Similarly, the reciprocal of b is the qth term of this AP because b is the qth term of this HP. And because c is the rth term of this HP, its reciprocal will be rth term of the corresponding AP. Now if I talk about this particular determinant, you have BC, CA, AB, and then you have PQR and 1, 1, 1. What I can do is, if I say ABC multiplied, divide. Again, ABC multiplied, divide. Again ABC multiplied, divide. Rest same, or I can say what you can do is rho 2 goes to rho 2 minus rho 3. Here we have p minus 1, q minus 1, r minus 1, we obviously need to use this. So build this setup, p minus 1, q minus 1, r minus 1, 1, 1, 1. ABC is going to come out common, right? ABC comes out common. you are left with BC upon ABC, which is 1 upon A, CA upon ABC, which is 1 upon B, and AB upon ABC, which is 1 upon C. Then you have P minus 1, Q minus 1, R minus 1, 1, 1, 1, right? After this, what I'm going to do is I'm going to basically say that rho 1 goes to rho 1 minus D times rho 2. So when you do that, you get 1 by A minus D times P minus 1, 1 by B minus D times Q minus 1, 1 by C minus D times R minus 1. Here you have P minus 1, Q minus 1, R minus 1, 1, 1, 1. What is this? See, 1 by A minus P minus 1 into D is capital A, 1 by B minus Q minus 1 into D is again capital A, and 1 by C minus R minus 1 into D is again capital A. So your first row is completely replaced by capital A, capital A, capital A. P minus 1, Q minus 1, R minus 1, 1, 1, 1. Whenever two rows of a determinant are same, its value is 0. Okay? So the value of this determinant where A, B, C are the pth, qth and rth terms of this HP is actually equal to 0, and that's how beautifully it's dealt with. How harmonic progression concept actually comes into picture and helps you evaluate the value of this reciprocals, use all the operations and hence get the answer by the properties of determinant to be equal to 0. Now it says if capital X, capital Y, capital Z are positive numbers such that Y and Z have 1 and 0 at their units place. Okay. If Y and Z have 1 and 0 at their units place and delta is this determinant, if this is divisible by 10, then X has at this units place what? So basically X, Y and Z are being divided by 10 and the remainders that are left are actually given to you. When Y is divided by 10, you get what? Say, when X is divided by 10, you get 10x plus lambda. I don't know what is the remainder, let lambda be the remainder. When Y is divided by 10, you get 10y plus 1 because it is given that 1 is kept at the units place when Y is divided by 10. And when Z is divided by 10, you get 10z plus 0. Fine, I need to compute this lambda. Now this determinant is actually capital X 4, 1, but capital X is 10x plus lambda, 4, 1. Capital Y 0, 1, so 10y plus 1, 0, 1. And Z 1, 0, Z is 10z plus 0, 1, 0. I can break this up as 10x 4, 1, 10y 0, 1, 10z 1, 0 plus lambda 4, 1, 1, 0, 1 and 0, 1, 0. Clearly from here you can see I can take out 10 common. I am left with x, y, z, 4, 0, 1, 1, 1, 0. Plus, when you will be evaluating this very easily, you will be getting 1 minus lambda. Now basically, I can just think of it as some k. Think of it as some k, this is delta. So delta is basically 10 into k plus 1 minus lambda. Question says that if delta plus 1 is divisible by 10, it is already given to you that delta plus 1 is divisible by 10, then capital X has at its units place which digit? So if delta plus 1 you want, let A be a 3 cross 3 matrix such that determinant of A is 4. Suppose Bij is 2i plus j Aij, where I and j are varying from 1 to 3 and b is this, then determinant of b is equal to what? So what exactly is b? B matrix is, let's see what it is. The 1/1th entry of B is 2 to the power 1 plus 1 A11. So it is 2 square A11. Next similarly is 2 cube A12, 2 to the power 4 A13. Similarly the 2/1th entry is 2 to the power 2 plus 1 A21, 2 to the power 2 plus 2 A22, 2 to the power 2 plus 3 A23. And similarly you have 2 to the power 4 A31, 2 to the power 5 A32, 2 to the power 6 A33. This is your 3 cross 3 matrix B. What will be the determinant of this particular matrix? What is determinant of B? Let's compute that determinant. What would that be? Now you can see 2 square common in the first column, 2 cube common in the second column, and 2 to the power 4 common in the third column. So I can write this as 2 square, 2 cube, 2 to the power 4 common. You are left with A11, 2A21 and 2 square A31. Then here 2 cube was taken out common, so here you have A12, then you have twice of A22 and 2 square of A32. Clear? From here you took out 2 to the power 4 common, so left with A13, 2 A23 and 2 square A33. Fine. Now you can see 2 is common in the second row, 2 square is common in the third row. So you take that out common as well. This becomes 2 to the power 9. And then you take out a 2 common and a 2 square common, basically 2 cube common you take out. You will be left with A11, A12, A13. 2 has come out common, so A21, A22, A23. 2 square come out common, so A31, A32, A33, which leaves you with determinant of A. And that is given to be as 4, that is 2 square. So your answer is nothing but 2 to the power 14. And therefore, that comes out to be your very correct answer. Next question let's see is what? This determinant is equal to 0 if A, B, C are in AP, GP, HP or alpha is a root of this quadratic equation. Let's see. So over here you can very easily find out what all the operations can I apply. You can see third row is basically alpha times the first row plus the second row. So what I'll do is I'll say that row 3 goes to row 3 minus alpha times row 1 minus row 2. So when you apply this operation, you basically get what? A alpha plus B minus A alpha minus B, this gives you 0. Then you have B alpha plus C minus B alpha minus C, which again gives you 0. And here you have 0 minus alpha times A alpha plus B minus B alpha minus C. So what do you get? You get minus A alpha square, or you can just write it as this, right? So here you get minus of A alpha square plus 2B alpha plus C. Clear? Now, the first row and the second row remain the same. This is A, B, A alpha plus B, B, C, B alpha plus C. Of course, you can expand this along the third row. When you do that, what do you get? You get minus of A alpha square plus 2B alpha plus C times AC into B, AC minus B square. Or you can write this as B square minus AC into A alpha square plus 2B alpha plus C. This is the determinant, and the value of the determinant is given to be 0. This is 0 when either this is 0 or this is 0. B square minus AC is 0, that means B square is equal to AC, that means ABC are in GP, or A alpha square plus 2B alpha plus C is 0, which means alpha is a root of AX square plus 2BX plus C equals 0. So these are the two correct options in this particular question. Okay. Next question says what? If delta x is this, then talk about the value of a, b, c, d. Okay. So delta x is given to be a cubic polynomial to us basically. Now over here if I want to talk about the values of a, b, c and d, I am going to be interested in delta dash x. What would this be? 2x minus 5. Then you have 6x plus 1. I am differentiating every term on the first column. 14x minus 6. Rest two columns remain the same. This is 2x minus 5, 6x plus 1, and this is 14x minus 6. And here you have 3, 9, 21. Plus, now you are going to differentiate the second column. You have, this remains the same. What is this? X square minus 5x plus 3. Then you have 3x square plus x plus 4. And then you have 7x square minus 6x plus 9. And here you have 2, 6 and 14. And then you have 3, 9 and 21. Okay. Very easily you can see over here these two columns are same. The value of the determinant is 0. In fact, this determinant is also 0. So you are getting delta dash is actually equal to 0, which means delta is a constant. If delta is a constant, that means there is no non-zero coefficient of x cube, no non-zero coefficient of x square, no non-zero coefficient of x, only this constant term is present. That means a is 0, b is 0 and c is 0. So what is my function actually? It is equal to delta x equal d. What is d? You are going to get the value of d when you put x equals 0. If you put x equals 0 everywhere, you basically get the determinant 3, 4, 9, minus 5, 1, 6, minus 5, 1, minus 6 and 3, 9, 21. When you compute that determinant, you get the value of d, which comes out to be 141. So your very determinant or this function is delta x equals 141. That is your constant term to which my function is equal to, because ABC is going to come out to be equal to 0. Fine. Fourth question says delta AB is given to you like this. Okay. Match the entries in column 1 with entries in column 2. Let's do that. Okay. So over here you can see I can perform this row operation. Row 2 goes to row 2 minus a times row 1. Row 2 goes to row 2 minus a times row 1. And I can also perform row 3 goes to row 3 minus a square times row 1. Right. So what do I get? This is 1, 5 and 10. Then this is a minus a is 0. Then this is 4a plus b minus 5a, which is b minus a. Then it is 6a plus 4b minus 10a, which is 4b minus 4a. Then you have a square minus a square will become 0. Then you have 3a square plus 2ab minus 5a square. So it becomes 2ab minus 2a square. Right? This is 3a square plus 2ab minus 5a square. So 3a square minus 5a square is minus 2a square. So 2ab minus 2a square, 2 common ab minus a square. Then here what is it that you have? You have 3a square plus 6ab plus b square minus 10a square. So this gives you b square plus 6ab minus 7a square. Why? This is 6ab plus b square plus 3a square minus 10a square, which is minus 7a square. In fact, this complete expression can be boiled down to b minus a, b plus 7a. Right? You can just see this is b square plus 7ab minus ab minus 7a square. So b square plus 6ab minus 7a square. Same thing. I just broke the middle term, nothing else. Okay? Now you will obviously be wanting to expand this along the first column. So here when you do that, what you get is b minus a into b minus a whole square, b plus 7a minus 8 times, or 8a times rather, b minus a whole square. That is the value. So b minus a whole square comes out common. You have b plus 7a minus 8a, which is again b minus a. So you get b minus a whole cube. Clear? Therefore, over here what you have is that delta AB is coming out to be b minus a whole cube. Now if delta AB is this, delta AB is actually b minus a whole cube, a gets matched to S. Fine. Then you have delta AB plus delta BC plus delta CA. So delta AB is b minus a whole cube plus delta BC is c minus b whole cube plus delta CA is a minus c whole cube. Now you know that b minus a plus c minus b plus a minus c is 0. So this cube plus this cube plus this cube is 3 times b minus a, c minus b, a minus c. Clear? So this expression is coming out to be equal to this. This is t. So b gets matched to t. Okay? This is not plus, this is actually multiplication. 3 times of b minus a, c minus b, a minus c. Fine? So what is it that you basically have is this particular term is coming out to be equal to this, that we have got thrice of b minus a into c minus b into a minus c. Now you have limit delta x tends to 0, delta of sin x comma cos x. Delta of a comma b is b minus a whole cube. So delta of sin x comma cos x is cos x minus sin x whole cube. And when you apply the limit x tends to 0, you know cube is a continuous function. So this is going to become limit of x tends to 0 cos x minus limit x tends to 0 sin x whole cube. That is, limit x tends to 0 cos x is 1, limit x tends to 0 sin x is 0. So you get 1 minus 0 whole cube, which is 1 cube, which is 1. And on the other hand, limit x tends to, if I talk about the next one, that is pi by 2, again cos x minus sin x whole cube. This is going to be limit x tends to pi by 2 cos x minus limit x tends to pi by 2 sin x whole cube, which is going to give you 0 minus 1, that is minus 1 whole cube, which is minus 1. So you basically get C gets matched to P and D gets matched to Q. Understood? So over here, this is what we basically obtain. Now, once we have done this matrix matching thing, let's move on to the next question, which is let fx be equal to this. Okay. Statement 1, statement 2. So I need to actually rectify these statements, verify these statements. What is this given to me? Let's try to find out.